So in Chapter 5, Section 8, we're going to be talking about solving variation problems. So a couple of things before we get started. We're going to introduce a four-step process for solving variation problems. And I know that some of the variation problems that we've seen in the past are actually direct proportionality problems, and they can be solved using that method. Unfortunately, that method does not generalize well. So even though I know you can do that for certain problems, I strongly encourage you to learn this four-step process because, first of all, it works for every type of variation. And the second thing is we are going to recycle this process in Chapter 5 sections, in a later chapter with exponentials, where your intuition will not be as helpful, but the process, the algorithm is the same regardless of what's happening. So in general, to resolve a variation problem, we are going to do the following four things. So the first thing we're going to do is write the general equation for the type of variation. Two, we're going to substitute in the given values to the equation, so the only unknown in the equation is the variation constant k. We will solve for the unknown k. Three, we will substitute the value of k back into the equation from step 1. We're going to also take note, and we'll talk about this, it may be useful to save k into our calculator. And finally, step 4, we're going to use finally, we're going to use the equation to answer the following question. All right, so let's take a look at our first couple of examples. And before we do, we want to talk about some different types of variation. So if a situation gives rise to an equation of the form y equals k times x, we say we have direct variation. So if our two variables are related by a linear equation, we say that we have direct variation. So the phrases we want to be on the lookout for are y varies directly as or with x, or y is directly proportional to x. So if we see any of the phrases or any variations of the semantics of that, we know that our model then is going to be y equals kx. So this is what we're talking about in step 1. When we're reading these problems, we need to identify which type of variation, and then we're going to select the appropriate equation. So in the beginning, right now, we only know one equation. So let's go ahead and take a look at example 1 and run through the process. So example 1, let y be directly proportional to x. Suppose y is 6 when x is 18. Find y when x is 12. So our first step in this process, since we have direct proportionality, we know our model is y equals k times x. Step 2 is we need to identify an ordered pair, and our ordered pair is here. We know that when x is 18, y is going to be 6, and we are going to take the x and the y value and substitute them into the equation from step 1 and solve for k. So that gives us 6 is equal to k, which we don't know, times 18. Divide by 18, divide by 18, we get k is 1/3. Step 3 is we put k back into our equation. So we have 1/3 x. And finally, step 4 is we're going to answer the question. And we want y when x is equal to 12. So in this case, we're just going to put 12 in, which gives us 12/3, which is 4. So the value of y is 4. So a couple of things. I know this seems like overkill on example 1, and it probably is. But the point of this is to practice when it's easy. Essentially, all of our variation problems are going to be application or word problems. And we're going to do them all using these 4 steps. So right now, it's really easy to identify all the bits, and it becomes a bit more challenging when we have to think about it a bit more. All right, the next type of variation we want to talk about is inverse variation. So if a situation gives rise to an equation of the form y equals k divided by x, we say we have inverse variation. So the phrases we want to be on the lookout for is y varies inversely as or with x, or y is inversely proportional to x. So when we have an inverse variation situation, instead of having a linear equation, we have the reciprocal function, or k times 1 over x. So let's take a look at example number 2. So let y be inversely proportional to x. So our step 1, we have inverse proportionality, so y is equal to k divided by x. Step 2, we need to find our ordered pair, so our x and our y that go together. So in this case, we have when y is 9, x is 6, so we get 6 comma 9. And we use those values to solve for k. So we multiply both sides by 6, and we get 54 is equal to our number k. Step 3 is we put k back into our equation. So y is 54 divided by x. And then step 4 is we are going to answer our question. So we want y when x equals to 18. So that gives us y equals 54 over 18, which is going to be exactly the number 3. Let's take a look at our next one. So we're going to have what's called combine or joint variation. And this comes in several different flavors. So if we have y varies directly as or with the nth power of x, we're going to get a situation that looks like this. So we get y equals k, but times x raised to the nth power. So we can modify the types of variation that we've had. So notice it is once again directly, but now we're adding a modifier to the variable x. So it changes our variation equation from y equals kx to y equals k times x to the n. We can do the same thing with inverse variation. So y varies inversely as or with the nth power of x. So this time we would get y equals k divided by x raised to the nth power. Our last type of combine or joint variation is y varies jointly as or with x and z. So if we're not given any other modifiers, we assume when we're told jointly with nothing else that it is actually directly with both of those variables. So then our equation would be y equals k times x times z. So we're now familiar with several different types of variation. We can combine all of the different types of variation together in one problem. So let's make a few meta-observations about all types of variation. So for each type of variation, let's just kind of write down our equations. We had y equals k times x. We had y equals k divided by x. We had y equals k times x to the n. Y equals k times, or k divided by x to the n. And z equals k times x times y. So in every single one of these equations, we notice we have one variable, and in this generic case we used y or z, always on the left-hand side. Then on the right-hand side, what does every variation equation have? Well, every single one of them contains a k. So every variation equation is going to start off this way. What arithmetic operations are present in variation problems? Well, to connect the variable x to k, we are either multiplying or dividing. That's it. So in variation problems, we will never add and we will never subtract. So it will always be k times something or k divided by something. So we'll notice in the cases where we multiply, was when we had direct. The cases where we divide, we have inverse. So when we see the keyword direct, that means we're going to multiply by whatever that variable is. If we see the keyword inverse with variation, it means we are going to divide by that variable. We are then free to add any modifiers to those variables that we wish. So like powers, squares, cubes, cube roots, square roots. Anything you can dream up can be used as a modifier for any one of those variables. So this is a generic template that we're going to use to set up these types of equations. All right. So let's take a look at example 3 now. So let y be inversely proportional to the square of x. Suppose y equals 3 when x equals 6. Find x when y equals 27. So our first step is to write down our type of variation. So our keyword that we notice this time is we have inverse proportionality. So they always start off as y equals k, and then it's inverse proportionality, so that tells us we're going to divide. But then we have an extra modifier. It is inversely proportional to the square of x. So we have x, but we've modified it with an exponent of 2. So now we have our variation equation. The rest of the steps are the same as all the ones we've been doing. All of the work is really in step 1, writing down the correct variation equation. Everything else is just turning the crank, doing steps 2, steps 3, and steps 4. So step 2 is we identify our ordered pair, which is 6 and 3. So we put them in, and we get 3 is equal to k divided by 6 squared. So 3 is equal to k divided by 36. We multiply by 36. We multiply by 36, and we get 108 is equal to k. So we then put k back into our variation equation from step 1. So y equals 108 divided by x squared. And finally, step 4 is we want to answer the question. So step 4, we want to find x when y is 27. So we want x when y equals to 27. So we need to solve the equation 27 is equal to 108 divided by x squared. So we multiply both sides of our equation by x squared, and we get 27x squared equals 108. So then we minus 108, we minus 108, and we get 27x squared minus 108 equals 0. We factor out our GCF of 27, giving us x squared minus 4 is equal to 0. And we factor our difference of squares as x minus 2 times x plus 2 equals 0. So then our two solutions are x equals 2 or x equals to negative 2. It's worth noting we could have also used the square root principle. So at that stage, when we had 27x squared equals 108, we could divide by 27, giving us x squared equals 4. Taking our square root and not forgetting our plus or minus, we get x is equal to plus or minus the square root of 4, which is plus or minus 2. So notice both ways give you the same equivalent solution for x regardless of how we set this up. All right, so now let's take a look at a few examples when we're doing this. So when we're solving variation problems, instead of using the generic variables y and x, it is often best to use descriptive variables of what we're talking about. It will make it easier in step 2 when we have to identify our ordered pairs. It will also help us make sure that we're putting the right values in the right place. So example 4 reads as follows. The wavelength W of a wave varies inversely as its frequency f. A wave with a frequency of 100 kilohertz has a length of 118 meters. What is the frequency of a wave with a length of 128 meters? Round your answer to the nearest tenth. So step 1, we need to identify our type of variation. So our keyword is it varies inversely. So W varies inversely as F. So in terms of our equation then, W is equal to K times, varies inversely, divided by F. Because we have inverse variation. So then for step 2, we are looking for a frequency and a wavelength that pair up. So we have that a wave with a frequency of 100 kilohertz, that's going to be here, is going to have a length of 118 meters. So we have our 118 that pairs with 100. And we put those into our equation and solve for K. So 118 is equal to K divided by 100. So we multiply by 100, we multiply by 100, and that gives us K is equal to 11800. Step 3 says we put K back into our equation from step 1. So W is equal to 11,800 divided by F. Finally, step 4 is we wish to answer the question. So we want to know, well, what is the frequency, so this is what we want, when the length is 128 meters. So we want F when W equals 128. So we put 128 in for W. Solve for F. Multiply both sides of the equation by F. We get 128F equals 11800. We divide by 128. Divide by 128. And we get 11800 divided by 128. We get this value, but in the original problem we were asked to round our answer to the nearest tenth. So we look at our tenths, and 8 says it rounds up. So F is approximately equal to 92.2. All right, so let's just recap for a second kind of what happened. So the variation problem is resolved using the same process we did for all the ones where it wasn't an actual application problem. So we find our keywords that tell us how the variables are related. We write down our equation, identify our ordered pairs, and we're off to the races. So it's really the same process that we've been doing the entire time. All right, let's take a look at example number 5. So the stopping distance d of a car after the brakes are applied varies directly as the square of the speed r. If a car is traveling 30 miles per hour can stop in 50 feet, how many feet will it take the same car to stop when traveling 36 miles per hour? So we start with step 1, and we have the stopping distance d of a car after the brakes are applied varies directly as the square of the speed r. So we have d, or stopping distance d, varies directly as the speed r with an extra modification as the square of. So we start with our stopping distance d is equal to k, because all variation problems always start out with equals k. And then we have direct variation, so that tells us we're going to multiply by the speed r. But it's not just the speed r, it's the square of the speed, so r has to have an exponent of 2. That is our variation equation for this problem. So now, step 2, we need an r and a d that pair up. So if a car traveling 30 miles per hour can stop in 50 feet, so r is our speed and d is our stopping distance. So we're going to have 30 and 50. And we're going to put those into our equation to solve for k. So that gives us 50 is equal to k times 30 squared. So 50 equals 30 squared is 900 times k. We divide by 900, divide by 900, and that gives us k equals 50 goes into 900 18 times. So we get 1 over 18. Step 3, we put k back into our original equation. So we get 1 over 18 times r squared. Step 4 is we want to answer the question. So how many feet will it take the same car to stop when it is traveling 36 miles per hour? So we want d when r is equal to 36. So that gives us d is equal to 1 over 18 times 36 squared. Well, 36 squared is 36 times 36 all over 18. So 18 goes into 36 twice, and 2 times 36 is 72. You don't have to do the arithmetic by hand. You can just type it into your calculator, and you'll get the same thing. So the stopping distance would be 72 feet, right? So when it was going 30 miles an hour, it took 50 feet to stop. When it was going 36 miles an hour, it took 72 feet to stop. All right. So example 6. The gravitational force F of a point mass is directly proportional to the mass of the object m and inversely proportional to the square of the distance between the two objects, r. If the force between two objects is 100 newtons when the objects are 20 meters apart and the mass of the object is 16 kilograms, find the force on a particle of mass 6 kilograms that is 8 meters from the point mass. So, a couple of observations that we're going to make. We have the gravitational force F is directly proportional to the mass and inversely proportional to the square of the distance between the two objects. So direct proportionality means we are going to multiply. Inverse proportionality means we are going to divide. And remember, we are only allowed to multiply and divide. We're not adding or subtracting anything. So we start with F is equal to K, because that's how every proportionality problem starts. And then it's directly proportional to the mass, so that's times m, and inversely proportional to the square of the distance between the two objects, r. So we multiply by m and we divide by r. But it's not just r, it's the square of the distance between the two objects. So that means we need to square the r. So this variation problem is a mixture of direct variation, inverse variation, and combined variation. You can combine all of your rules in one problem and have as many different things vary as you want. This example had 2. In theory, you can do it for 1,000,000 if you just keep adding the appropriate descriptors. So that's our step 1. Step 2 now, we have 1, 2, 3 variables. So we're going to need an R, an M, and an F that are going to go together. So if the force between the two objects is 100 newtons, so that's our F, when the objects are 20 meters apart, that's our R, and the mass of the object is 16, that's our M, we now have an R, an M, and an F that go together. We can use these to solve for K. So we plug all of these into our equation. So 100 is equal to K times M, which is 16, divided by R, which is 20 squared. So that gives us 100 equals 16K over 20 squared is 400. So we solve by multiplying both sides of the equation by 400. That gives us 40,000 is equal to 16K. We divide by 16, divide by 16, and that gives us 40,000 divided by 16 is 2,500. So then we put our K back into the equation from step 1. So we have 2,500 M divided by R squared. So now finally, what were we asked to find? So we want to find the force on a particle of mass 6 kilograms that is 8 meters from the point mass. So 4 is we want F when M equals 6 and R is equal to 8. And we put all of these values in, 2,500 times 6 all over 8 squared. $2,500 times 6 all over 8 squared gives us 1875 over 8, but we want a decimal. So we get the force is 234.375 newtons.